Hello everyone, and welcome to our episode 4 of the Advanced Zenoh tutorial. So today we are going to cover a few other aspects on Zenoh, focusing essentially on scouting and routing for most of it. So let me share my screen and we'll get started in a moment. Meanwhile, as you can read from the chat, slides will be available after the presentation on slide deck. And if you have any questions, please ask them as they come. Quick recap. So fourth episode, last episode, we covered once again storage alignment. We went through plugins, and more importantly, the aspect that you have to consider when dealing with the lack of API compatibility in Rust, and some of the mechanisms that you can use in Zenoh, especially with the required configuration flag, to make it clear when a plugin is not being loaded, perhaps because of some API issue. Then we looked at liveness token, we looked at connectivity event, and we looked also at how you can change QoS on the fly by configuration. Okay, so today, so first things before jumping into the content of today's webinar, I wanted to give you an heads up. So a few evenings ago, I started putting together an awesome Zenoh. Why? Well, because there are an increasing number of projects that are using Zenoh, that are building Zenoh, that are making verticalization of Zenoh for certain domain. And I thought it was good to have a home for all these projects. So, as you know, usually you have awesome XYZ and so on and so forth. So I decided to make this awesome Zenoh. There are already quite a few projects listed, but anything you contribute or anything you want to be listed, just make a pull request. It will be reviewed very timely. Other reminder, as we go through the webinar, we keep extending the Zenoh Swiss Army knife. As you will see on the Zenoh Awesome, actually there are similar applications that were done by the community in Python, and you will have link in the Zenoh Awesome. But otherwise, is again a good example to experiment with Zenoh and try to familiarize with some of the concept, and then perhaps look at the code and see how you can achieve certain mechanism. You can clone it, build it, run it, and use the help to get additional information. But let's start with the first topic of the day, which is the overall topic of discovery. Okay. And discovery, as we will see, has roughly 2 dimensions, right? Because as I often say, we need to discover the who, so what makes our network, and then the what, which is what are the subject matter that we are interested in, and as a consequence, how we can make sure that information, and as we will see, or queries, is routed to the right place. But let's get started in order because before being able to talk, we have to see with who we can talk, who is around. And the role of understanding who is around in Zenoh is kind of addressed by scouting. So what is scouting? Scouting is about discovering endpoints, where endpoints could be across, as we have seen in the previous webinar, across multiple communication technology, right? As a Zenoh application, I could expose endpoint in UDP, in TCP, serial, Unix pipes, and so on and so forth. So here I will just refer to endpoints without specifying what kind of a link we are using to communicate, okay? But again, scouting is about discovering endpoint from other application so that I can bootstrap Zenoh session. So I discover, establish a Zenoh session, and eventually start to do something useful. Now, you can configure, obviously, this endpoint explicitly, and as a consequence, control the resulting Zenoh network. And there will be more of this, okay? You can use scouting to automatically establish session between discovered Zenoh runtimes, and actually you can mix the two approaches, okay? The other important things to understand is that scouting is actually technically not part of the Zenoh protocol. We use scouting in order to bootstrap the Zenoh protocol, Because in Zenoh, in order to do anything, we need to establish a session. To establish a session, we need an endpoint. And the question is, how do we find out the endpoints of runtimes that are sitting, somewhere? And we will see what that somewhere could be, depending on the scouting that you are using. If you've used Zenoh, perhaps the scouting mechanisms that you've used, especially when running on a local area network or when playing around in your laptop, is what we call multicast scouting. Okay, if you have an environment in which multicast is enabled, then, and if you enable multicast scouting in Zenoh, then what happens is that at runtime, a Zenoh application will send scout messages. And the scout message include a signature that we call what, where this what essentially tells what you're looking for, what might be an application looking for. Well, depending on your application, if you're a client, perhaps you're looking for routers or for peers, because you need to establish a session in order to be able to do anything, right? If you are a router, or maybe if you're a peer, maybe you're looking for peers or other routers. But in any case, this what is controllable. Okay. So whenever it's an application for which multicast scouting is enabled receives an hello, right? Then it will answer. Actually receives a scout. It will answer with a hello message, telling what it is. Okay, so what am I? And this hello message will also include locators through which this application can be reached. And usually the locator are in order of preference. Okay, so typically, if you provide locators for, let's say, TCP, UDP, and something else, I will pick the first locator and establish a session on that locator. That also depends on the configuration, because perhaps, there are other aspects that might impact this, but that's, let's say, the simple story. Okay, and what am I, again, can be a description of the role that I play. So, am I a router, am I a peer, am I a client, and so on and so forth. Now, let's look at the client default behavior. Okay, so if you have a Zenoh application that is running on client mode, okay, then what it will do, it will try to scout by default for routers. And again, that's the default behavior. If you want a client to scout for peers, you just have to change the configuration to make sure that the what of the scout includes routers as well as peers. But off the shelf, client only scout for routers. Okay. Now, if a client doesn't find any router within a configurable delay, then actually your application will exit with an error. Okay. And even this is configurable, by the way. We will be able to take a look at this in the configuration. Notice that a client needs, by default, either a peer or a client to operate. Why? Well, because as we've discussed in previous webinar, a client is not self-sufficient. In order to communicate with the rest of Zenoh application, needs a node that mediates that communication. Okay, this is why by default, if you cannot open a session, your client application will exit with an error, say, hey, couldn't find anything. Things are slightly different for a peer. If you are a peer, okay, by default, your scouting will be looking for other peers and routers. Okay. Now, notice that as a peer is self-sufficient, it doesn't need anything else in order to be able to have the potential to communicate. Then actually, even if you don't discover anybody around, that's not considered to be an issue or an error by default. This is sometimes confusing for new Zenoh user, but think about it for a moment. As a peer, you are cool, right? I mean, you don't need anything else. You don't need anybody else. You are happy even alone. If somebody else comes around, you might discover, establish a session, and engage in interesting exchanges. But otherwise, you are self-sufficient. You have the potential to communicate. And this is why, by default, even if a peer doesn't discover anybody, then that is not considered to be an issue or an error. So obviously, if we go back for a moment to client, right, the client behavior might seem extreme, but if you think about it, if a client cannot hook into something, is not fully operational. Okay. Um, Now, obviously, you can control for how long you will be looking for something, so that if you are starting a system, you can tolerate. You don't need to have any specific startup order, but you can have sufficiently reasonable scouting interval, so that eventually the client will find a router or a peer, depending on the configuration. But for peers, it makes absolute sense that whether I'm alone or there are 1 zillion other peer, I mean, actually, with respect to me and my potential to communicate, doesn't make any difference. So even if I don't discover anybody, that's still okay. Your session, will consider as being open, and so on and so forth. Then for router, actually, router by default don't do any scouting. Okay, so that's the default behavior. If you want the router to scout, then you'll have to enable it by hand. Why do we have that off-the-shelf behavior? Well, because if you think about it, very often, right, you might have peers running on a network where they might be able to discover each other and discover routers by multicast scouting. You will want peer to communicate peer to peer, and perhaps discover routers and have session with the router, and then use the router to route data, perhaps either across the internet or across subnetwork. But in general, you will want to configure the topology of your routers very carefully, depending on the system that you are building and the kind of network you need to cross. Okay. So how do you configure multicast scouting? So this is the default configuration. So if you take the Zenoh, if you check it out from GitHub, this is what you see by default. But let's look a little bit through the configuration. So this is the scouting section, okay, where you have some the timeout for which for 3 seconds you'll try to scout, and you will scout every 500 milliseconds. That's what it means. So essentially, that means that you will send roughly between 5 and 6 scout messages, okay? And after 3 seconds, you'll time out scouting. Whatever you have discovered, you consider that your scouting is over. Then there is a scout call at the session level that you can run. We will see that in a moment with the Zenoh Swiss Army knife. Then, as I said, there are multiple ways of doing scouting, and so far we have covered multicast scouting, which you can enable or disable. And by default, multicast scouting is enabled by default. It uses the port 7446 and the multicast address 224.0.0.224. The interface is chosen automatically, but you might want to specify a specific interface over which you want to do scouting. And you can also control the time to live. Time to live is, how many hop your scouting message will be routed by the IP network. Then another important aspect is to who do you auto connect. So suppose that I'm a router, okay? What this says is that if you are a router, you don't auto connect to anybody, okay? While if you're a peer, you automatically connect to routers as well as peers. And if you're a client, you automatically connects to routers. Again, this is the default behavior that you can customize. So you could decide, for instance, that maybe a peer only auto connects to peer, and you want to explicitly provide the session for the router, for instance. Or you could decide, that for how you've configured your interface, you might want also routers to auto connect to routers, whatever. Yeah, and I think that, and then you have whether or not you are listening. So because you can scout, right? Because you are searching for something. Imagine a client. A client wants to scout and then wait back, hello, but it doesn't want to answer to scout. And the listen allows you to control precisely this aspect. So in a way, it is as if am I discoverable? Okay. If it's true, it's yes. If it's false, it's no. So I can snoop around, but other people cannot snoop me. That's one way in which you can see it. Okay. Now, multicast scouting works nicely if you're on a network, obviously, that supports UDP multicast. There is a typo, so it's supposed to be UDP. I'll fix it before distributing slides. Sorry for that. But that isn't always the case. Sometimes multicast is not configured. In other instances, actually is forbidden. And then, yet in other cases, that's not the behavior you want, right? I mean, imagine I have multiple devices. Um, I mean, maybe I don't want to just discover all of them and establish session to all of them. Okay, or maybe that might be one case. This is why in Zenoh you can provide explicit locator. Or maybe um, in the network I'm running, actually there is no multicast. Okay, imagine I am on a private 5G network. Okay, how do I do? I want still maybe want to have some peer-to-peer communication, but perhaps I don't have multicast. How do I discover the other peers? And there are also some scenario in wireless Wi-Fi network in which multicast is just not enabled. How do you easily do discovery? Think about a data center case. I mean, I'm deploying, as we have some customer, and we also have an infrastructure running on the cloud. How do I, set up my network so that I don't have to fix the locator by hand? I mean, that's very error prone and not very nice. So for this, we have another kind of scouting, which is called gossip scouting. And in order to understand how this works, I just want to share a simple example of one instance of scouting. But obviously, this is a more generic, from this we'll generalize. So let's assume that we have a router that we'll call R and a certain number of peers. In this case, I show 3, but could be n peers, okay? PI, PJ, PK, whatever. And each of these peers has been configured with the locator of the router, okay? Again, as they are peers, even if the router is not running, that's fine. I open my session will succeed, and eventually it will periodically try to reestablish a session at this locator with an exponential backoff. So eventually, if the router is started, the session will be established, okay, with the router. We also assume that we have the default gossip scouting configuration in Zenoh. Okay, so if we enable gossip scouting, what happens? So when the peer PI is started, it opens a session with R. Okay, and then when the peer's PJ is started, he opens a session with R and actually receives the locator for PI. Okay. Now, why didn't PI receive any locator? Well, because we assumed, right, that before there was just R and nothing else. PI comes, open a session, but no other application is running or has a session with the router. So there is nothing for the router to share with PI. So then the PRJ or PJ arrives, opens a session with R, and he gets the locator for PI. As a consequence, what will he do? He will establish a session with PI. Now PK arrives, okay, opens a session with the router, and the router gossips around the fact that he knows PJ and PI. And so PK will establish a session with PJ and PI. What does that mean? It means that now PI, PJ, and PK will be able to communicate peer-to-peer, and then potentially when crossing, the boundaries, suppose that the router also provide or has internet connectivity and maybe has a session with some other router running goes nowhere, then they will only use the router to communicate outside of this subsystem potentially. Okay, but this is the basic idea of gossip. The basic idea of gossip, okay, and in this case we had router gossip, but peers can also gossip. Okay, but the basic idea is that whenever you establish a session with me, not only I will tell you hello, okay, but I will tell you who I know, okay? And as those who I just learned about told me also who they know, eventually you'll be able to do the closure of the network. And if this is what you want, establish session with all discovered node. without any multicast support. So that's very handy. And if we look at the default configuration, in Zenoh, gossip scouting is enabled. You don't have multi-hop, okay? And that can be enabled or disabled. And then you can, I think the interesting part is the auto-connect. Notice that the router, again, will not auto-connect to other routers, but peers will auto-connect with other routers as well as peers, okay? And also notice that a peer will always connect to a router and always connect to another peer when discovered, which is quite important, okay? So that's the default configuration. Now, if we put all of this together, it means that actually for maximum flexibility, you can use at the same time multicast and gossip scouting. Now, you can properly leverage the target to avoid that unnecessary scouting information is sent. And for instance, if you were to implement the use case that I just showed with the animation, you would rather want to have the auto-connect router appear as showed here, okay? So doing some recap, scouting is about establishing Zenoh network topologies. The resulting network will be used to route data, okay? But how data is routed is controlled by another mechanism. Okay, so here you have example of potential topology that you could have for a Zenoh network. And again, this is a click. This is usually what you would get if you have multicast scouting. We saw, for instance, in this case, we end up also with a click, okay? But again, you have no limitation, and you can combine multicast, gossip, and explicit locator actually to play around. Okay, so the Zenoh Swiss Army knife has been expanded with scouting. So, for instance, if we do scout and we scout for 1 second, you see actually that there are quite a few things running on the network right now. Okay, so there are quite a few things running on the network right now. And the other nice things is that not only you can retrieve the things running on the network, but for instance, you could even retrieve the graph. So let's try this, okay? So if you do, actually, I should increase a little bit, otherwise this will be a little bit unreadable. So let me redo the scout for 1 second. So notice that, let me scroll up. In this case, right, you get the Zenoh ID, the kind, and the locator. Okay, this is actually myself probably running here. Here you have another peer, and these are all the locators that are available. That's a router, okay, and all the locator to which is reachable, that's a peer. These are probably things running on my colleague's machine. You can also see from the IP addresses. They are all different. So this probably has even 2 network cards, okay? So that's one of the things. And actually something else you could do is just to list the Zenoh ID that are available and learn what they are about, okay? And let's see, let me try something else. If we do a scout, oops, 1 second. Okay, so what I want to do now, let me try this. I'm gonna try to fetch the topology seen by this router. So what I can do, I establish a session with that router. Actually, I want to do like this. Oh, yeah, I had copied the locator. And then we do graph. And I need, if I want the view from this router, we can do like this. Yeah, so in this case, you see that this router, in terms of topology, there are no other router. We get the dot file, so it's a single router with all that is running on the network. But as you will see, if you look at the code of the Zenoh Swiss Army knife, there is in fact a specific key. Well, maybe I can even show you. Router. Yeah, this is the key. So this is the key that you can use to fetch the graph that is used to route by the current router. Okay, where this is the ZID of the router from which you want to see the graph, or how it sees the routing graph at this present time, from that specific place on the network. On theory, all routers should eventually see the same graph. Otherwise, we wouldn't have convergence, and this is what happens. But the ability of being able to query for a specific routers allows to check that aspect too. But actually, I believe that let me double check. Yeah, I think actually for some reason that the screen wasn't shown. So let me just show what I was doing. So let me scout. So here you can see the scouting and all the various nodes that I discovered. Okay. You can see the ID, the kind, and then the locators. Okay. Then what I did, there was actually this node. Let me show up here. There is a router, okay? And so what I said, okay, fine. If there is a router, let me check what is the graph that it sees. And maybe that router, there we go. Yeah, I had added a spurious L. So that router, in fact, is alone, okay? And that uses the key that I was precisely showing you before, which is this one, okay? Okay, let's go back to our slides. And let's try to look now at discovery, okay? So the Zenoh protocol at its heart is really a routing protocol, and a routing protocol that works on named data, okay? And the underlying topology, so what we established, again, either through scouting or by a combination of multicast, gossip scouting, and explicit locator, just defines the constraint, right, the topology on how we might let data flow across the Zenoh network, okay? And so in a way defines the constraint on how data and query will be routed to reach their destination. Now the question is, in Zenoh, how do we figure out where data or queries needs to flow, okay? That is done through declaration, and there are three kinds of declaration in Zenoh. In Zenoh, you can declare a key expression, okay? And a key expression, or declaring a key expression, does nothing else than defining an association between the name represented by the key expression and a very small numerical ID. And I will show you this in action in a Warshard capture in a moment, okay? Then you can define declare subscriptions, or you can declare queryable. So you see that here, there is nothing like declaring a publisher. Why? Well, because a publisher technically is not, or the information associated to the publisher is not needed to know how to route data, right? When you publish, you are saying, well, I'm associating with this key, this value. And it's at that point that then, based on the name of the data, so the key, we need to be able to know how to route it. Same things when you do a query. When you do a query, we look at the key expression and read the information about queryables to know how to route this data, okay? Other important things is that notice that the association of a key expression ID is unique within a session. So there is a session between two Zenoh application, A and B. The key A/B will be 15 within this session. But then if B and C have another session, right, the key A/B might be 18 in that session, okay? So that's also quite important. Okay, let's try to grasp the key idea behind declarations. And I hope that people will understand that for how Zenoh was designed, right? In general, you are not supposed to know how many subscribers there are because that's inherently non-scalable. You are not supposed to know how many publishers there are. Then obviously you can use liveness token to keep track of those, and take a look at the last webinar to see how that can be done. But so if we go back to declarations, whenever you declare a publisher or a queryable, declarations are distributed over the Zenoh network. Zenoh might decide to generalize subscription downstreams, but might also decide not to propagate them alone at all. And you'll see more later about this. Okay, now let's assume that we have a series of subscribers, okay, as indicated here in this diagram. And let's assume that we had subscriber for AB, subscriber for AC, a subscriber for B/A, B/C, CA, CB. Okay. Now they were declared. Now let's see what happens in terms of declaration, and let's try to build the intuition behind this. Okay. So when this is declared, okay, Zenoh will actually propagate to the next hop this declaration. Let's assume the next hop was a router, okay? And actually, let me go back, okay? But potentially, you have no clue of what will be declared to the rest of the network. The intermediary node, it's free in a Zenoh network to say that actually it declares C star, okay? So if you look from here, let me go back. It received declaration for CBCA, okay, AB, AC here, B, CBA, and so on and so forth. But then when declaring on the other link to the rest of the system, it could generalize. And this is something that Zenoh can do under the hood. So, often I see on Discord, and the last was probably last night, a question from user on Discord saying, how can I see how many subscribers do I have? Well, you can't. And that's done intentionally. This is done to ensure that we can have better scalability. Okay. And so obviously this will continue to propagate, and you can understand that actually this reduces overall the discovery traffic. Okay. Now, the question is, but hold on a second. That's great, but I really just don't want to receive any declarations, because if you think for a moment, there are few reasons why we might want to receive declaration. If I'm someone that routes information like a router, I need to receive declarations, but in fact, even for an application, but I need to receive declaration in order to understand, depending on my session, where I need to forward data. Okay, because if I receive a declaration for A star on this session, I know that's over there is interest for something that matches A star. And so if I ever receive from some other session, a key AB, I know that this will have to be routed over here because there is interest for A/star. Okay, but maybe in some circumstances, I actually don't even want to know, right? Because maybe I'm so constrained, I'm just a super tiny microcontroller that publishes, few sensor data every so often, that I don't be bothered to know if, there is anything that matches what I'm publishing. I will just send data in any case, and the rest of the system will decide what to do with it, okay? So as we will see in a couple of slides, that actually can be controlled and can be controlled by interest. But while remaining on declaration can be aggregated automatically by Zenoh, and Zenoh plays around with it, or else you can control aggregation by configuration. And essentially, what you can do is to define which set of key needs to be aggregated to a generalized key expression. Okay, this is what you can do in the configuration of Zenoh. Okay, otherwise you are giving the hand of Zenoh, and Zenoh will take care of it. But again, the bottom line, and I want to go back, please. Keep this transition in your mind. The bottom line is that by default in Zenoh you have no clue, and that's by design, of how many subscribers there are matching a given key expression. And even on the publisher, we saw the matching status last time, right? In the publisher, you're able to know if something is matching, right? But you have no clue of how many are matching. And that's very important because of scalability. Okay, so let's do a little bit of Wireshark now. I want to show you a little bit more in details how this looks like. And in fact, I have a capture here of, and then maybe we can do another one live if necessary, but I wanted to go through this. So here you have the session opening, and then the first declaration. Oh, by the way, so actually, let's redo the capture, because I think it will be more interesting if we see that. So what I'm gonna do, I'm gonna start here subscriber, always with the Zenoh Swiss Army tool. Okay, so subscribe. And here we are going to do, so let me start capturing on loopback. By the way, I want to do this slightly differently. I want to listen on TCP 1.0.0.1. Oh, yeah, because in this we have to pass it as a list of strings. What's the deal? Oh, because I've probably already yeah, okay. I've already something running there. Let me check what I've running here at that port. Just a moment. Yeah, here it is. Okay, I had a bunch of applications running on my machine. So the problem should be solved. I have a bunch of publisher and subscriber. Yeah, so now should be fine. Let's see. Up. Yeah, that's good. Okay, problem solved. And now what we're going to do, we're going to do like this. And we're going to publish. Okay, so let me start here, the capture. So you see there is nothing going on right now. Okay, and then I'll start a publish. So the key is demo/foo. Okay, so that's done, and this application is completed. This has received the hello, so everything is in order. Okay, so let's see what happened. There is an open. Then, well, so this is running with default configuration. So this OAM is sharing all the locators. So actually, let me show you how to get rid of this, for instance, because sometimes that can also be fairly sizable. So if I do this, I will ask just to listen on a single locator as opposed to all the available locators. And that OEM will become much smaller, because otherwise I will be exposing locator for all of my interfaces. Oh, let's do like this. So we will have a clean capture. Let's call this LO3. Okay, good. So we have our open, and then here we have an OEM and some declare. But let's look at the declare, because that's what I want to show you. So if we look at the declare, we see that this declare is declaring a key expression, and it's associating the ID1 to the key demo foo. Okay, and then it's declaring a subscriber. And notice that the subscriber, hopefully this is sufficiently visible, is declaring a subscriber for the ID1, but ID1 in this context is demo foo. Notice also that the way in which on the wire key expression are represented, there is always a scope, which is an ID, and a suffix that is a string. So we can actually detect prefixes that are used commonly, compress them to a small ID, even if you don't declare a key expression, and then use it when sending data. And if we look at the data here, right, you see that actually this is it's pushing data for what? For the key expression 1, which because of the declaration, we know it's a demo slash foo. So if you recall, I was mentioning over the webinar that actually the string rarely goes on the network. And in fact, it goes on the network, the string associated to the key expression for the declaration. But then, as much as possible, we use small identifier. And as these identifier are unique to the session, right, usually they are, a byte long. So that's very efficient. Then obviously it depends how many key you register, but with 2 bytes you will be able to cover 2 to the 14, because every byte for how the string this ID is encoded is a VLE. We can only use 7-bit. Okay, so 7-bit for the first byte, 14-bit for the second byte, and 21, and so on and so forth. Okay, so let's go back to the slides. And let's start covering interest. Okay, so we've seen that by default, right, we distribute declaration for subscribers and queryables. And the point is, how can we control how far these declarations are distributed, and how can an application tell whether or not they want to receive this or at Zenoh runtime this declaration? That can be done with interest. And by default, interests are automatically asserted when declaring a publisher or a querier. So when you declare a publisher in Zenoh, the publisher declares an interest that says, hey, whatever is upstream, please inform me on any declaration that matches my publication key expression. Same things for a querier. Why is that done by default? Because that way the publisher can avoid sending data on the network if there is no matching interest. Okay. On the other hand, whenever you use a put or a get, no interests are expressed. So that also tells you that if I don't want to receive interest because in any case I don't want to be bothered to know who am I matching. I'm going to publish periodically anyway, and I want to minimize the memory that I get because I don't want to receive these matches, right? Then I just use put and get. In that case, by default, I receive no interest. So what does that mean? That using put and get, right? If we have an application that publish data using pub, or does query using get, let's say on a key A1 or W1, this will always be sent to the router, and it will be the router who has received the declaration that will decide whether this information has to get forwarded or not. And in any case, as you understand, the interest allow you to decide and to control the trade-off between how deep you distribute declaration versus how blind you are when sending data upstream. Okay. Now, if on the other hand we had created a publisher for the key A1 and a publisher for the key W1, then in that case the publisher would have caused the declaration of interest for A1 and the declaration of interest for W1. As a consequence, whenever the router would receive declaration that matched this interest, would have shared declaration that actually indicate to the publisher that indeed there are matches. Once again, you don't know how many, you don't know the exact details of the match, but you have sometimes a generalization of what is matching with you, which in other terms, it's all you need because it tells you it's worth sending data to next stop because someone is interested in receiving it. Okay. And again, so you still have, in a way, minimal amount of data in terms of meta information that is shared with you, but some meta information is shared, and you can control this with interest. How does the interest message look like? Well, this is the structure of an interest message. Okay, that's actually a message that we introduced with V1, the V1 protocol version, and this is essentially the interaction diagram that describes how interests work. Okay, but let's keep moving because we have one more topic to cover today before concluding this webinar, and time is running. Routing. Okay, so we've seen how we establish topology, right? We've seen how we propagate and how to control the propagation of declaration on a Zenoh network. And now we have the topological constraint. We know essentially from where are the interests, and now the question is, how do we route information, right? Which algorithm do we use? And in Zenoh, you have two routing algorithms that can be used that are called link state and peer-to-peer. Okay, link state can be used to route over arbitrary connected graph, like the one that you see here on the top, while peer-to-peer can only used if every node in your graph is directly connected to every other node in the communication graph. In other terms, if your graph is a click, so it looks like this. Okay, that's the basic idea. So to give you an intuition of link state, the graph is maintained up to date on every element that takes part to the routing. And again, those could be peers, could be routers, although they constitute to different routing domain. Okay, but within a given routing domain, all the entities that are supposed to be routing data, they maintain a graph, and the view of the graph, so the topology, is maintained up to date by sharing link state messages. And then these link state messages are shared each time there is a topological change. What does that mean? A router crashes, right? Or a router that was connected, on this side, I had a session on this side with the router crashes. I'll inform the other routers to which I'm connected that this router crashed. Okay, so they can update their view of the system. And besides maintaining, a coherent view of the graph, what they do is essentially to compute the shortest path to every other node in the graph. And this computation is done in such a way that even if there are multiple paths from A to B that have the same cost, every node chooses exactly the same path. Okay, that's very important to remark. And then the shortest path is used to route data. So, every element has a routing table. I receive a push message for a given key expression. I know where I have to send it. Okay, so that's pretty straightforward. For peer-to-peer routing, the routing problem is trivial, right? Because in fact, I have a direct link with everyone else. So, I just need to know where there are the matches and then just forward data on the right link. Now, the interesting thing is that you can compose routing algorithm. Okay, so I can use different routing algorithms, and in fact, this is by the way, as we will see, the default for peers and routers. And additionally, peers and routers create different routing domain. So even if I was to use the same class of routing algorithms for peers and routers, they are still different domain, which is important for scalability. And we are working on providing you the ability of having an arbitrary number of routing domains, which is very important for super large scale systems. And so as you see here, I could use potentially link state. And again, this is the default, as we will see, for routers, and peer-to-peer for peers. Notice that I can have redundancy. So I can have, in a click of peers connected to multiple routers, okay? Or multiple peers connect to the same router, or the same peers connected to multiple routers, which is not shown here, but that will be yet another variant, okay? How do you configure routings? Well, you configure routing by with these parameters on the configuration, the Zenoh configuration. And again, by default, as I mentioned before, routers operate under link state and peers operate under peer-to-peer mode. As I just showed you, you can retrieve the routing graph. Okay, so here I was running, a little bit a graph with 5 nodes, and in any case, you can pipe this to to dot to create a PNG of the graph if you want. Okay, so that was the last things I wanted to cover for today. At this point, let's check if there are any questions. So just give me a moment to take a look. And if you have any question, do not hesitate again to ask them on the chat. Okay, so there is a question from Paul asking if we can have custom routing algorithm. Well, not as of today. I mean, this is a feature that we are considering, but it's not there yet. But the basic idea is to be able to define an interface that would allow you to have a custom routing algorithm. Now, in that case, you should make sure, obviously, that all the elements that belong to the given routing domain have the same algorithm. And as I mentioned before, what we're planning to do is just to add support for arbitrary level of routing, or arbitrary number of domains of routing, as opposed to having only two as we have today. Okay, there is another question concerning intents and whether those can be controlled by API. So as of today, the interest are no, there is no API to control interest. Okay, we might decide to expose it, but as of today, what control the interest is essentially the fact of using declaring a publisher or a querier automatically declare interest. And if you are using put and get as opposed to having a querier, then no interest are propagated. Maybe we'll consider to expose the API, but as of today, there is no API exposing interest to the or the ability of playing with interest at the application level. Okay, I see no other questions. So if that is all, I will thank all of you for joining this webinar, and I'll see you on July 1st. Take care. Thank you very much. Bye.